Hello friends and welcome at my channel. Today I would like to show you why the product rule is working if we're doing differentiation. So let's start. Imagine we have a function which is a product of two elementary functions, like even if we are considering f of x being equal to x squared, we know its derivative is 2x. We proved that. I can link it in the video as well. So we know that this is 2x, right? Or generally x squared prime is equal to 2x. Well, the question is, if we're working with the sum, we know we proved it. I'll link it also here, x squared plus, let's say, x. If you produce a derivative, we can separate it, we can apply the sum rule, knowingly that every summand that we are producing derivative of is differentiable, so we're getting to 2x plus 1. All right. Now the story is, if we're talking about that, is it also applicable for the product? I mean, if you're just only reciting the formulas, if you're only memorizing it, well, it's not very nice, right? Because you don't understand the point why it's happening. So what we try to understand here, we're trying to understand why it is working the way it is working. So, but first of all, let us see, we know for sure that the derivative of x squared is 2x. What will happen if we would rewrite x squared as x times x and try to produce a derivative of this product? Well, imagine we just do not know anything about mathematics and haven't seen the visualization of the product rule, which I'm also linking here, which is the same playlist. And we would say, well, we just assume it's the same as the sum, so we are producing derivative of x times one more derivative of x. And, well, the thing is, if we're having that, we're obviously getting into 1 times 1, which is obviously unequal to 2x. So that's the problem, right? So obviously, if we're considering the derivation of a product, we have to consider a different kind of computation. So what was the error? Where did something go wrong? You see, it is exactly here. So the derivative of product obviously is not equal to the product of derivatives. And this is what we want to prove. So imagine we have f of x equal to p of x times g of x. And we would like to produce, well, first of all, the limit of the product. Okay, so the question is, if we have a limit x towards, let's say, 3 of x squared times square root out of x, can we produce it? Sure, we just put 3 inside. We just have 9 times square root of 3. No problem here. But what will happen if we have a limit x towards 3 of x squared separately times the limit x towards 3 of square root of x separately? What will happen there? Well, you maybe see that if we're considering this case, we have no trouble either. So we have 3 squared, which is 9, times square root of 3. So obviously those two limits are equal. That's nice. What will happen if we're having a limit of x towards 0 of x times 1 divided by x? What is happening here? Well, the situation is, if x is 0, x is approaching 0, well, that's fine, but now we're considering just the expression x times 1 divided by x, and we can cancel it, so we have a limit x towards 0 of 1. 1 is just a constant value, right? So x doesn't influence 1 any further, so the answer is 1. But if we are now considering limit x towards 0 of x only times the limit of 1 divided by x, x towards 0, obviously you see we are in trouble, because as we remember, this is one of the bad boys. This limit is incomputable. So the whole expression is incomputable. There is no result here. So we got 1 in the first line and no result in the second line. Obviously, they cannot be equal. So what is our conclusion from here? Well, our conclusion is, if we are having two limits that we're working with, then we can only separate the product if we can make sure that those two limits do really exist. And if they exist separately, you can also take the product away apart. Okay, so let's put it here. So we call this one a product rule of limits. As you can see, we have a limit of f of x, which is given, which is a. We also have the limit of g of x, which is also given, which is b. And so if that's the case, we have the limit of the product, which is equal to the product of the limits, but only if those two limits do exist. We can also prove it like from the standpoint of the university mathematics with delta and epsilon proofs. Like I've been working with my playlist in German about continuity, but if you are a high school student or if you are a student of economics, you are not digging that deep. Even though I'm gonna link, once I've done this video maybe correctly, like with the standpoint of mathematical analysis, I'm gonna link it here and you can enjoy the real so-called mathematical proof at this point. But now it's absolutely fine to understand what goes wrong in these examples. Okay, so this is the product rule of the limits. Now let's move on and try to understand what is the product rule of differentiation. Product rule of differentiation. Well, the idea is, imagine you have f of x equal to, let's call p of x times, I don't know, k of x or something, and we would like to produce its derivative. So it is f prime at xo equals to a limit x towards 0. We got p of xo plus h times k of xo plus h minus p of xo times k of xo divided over h. Alright, so that's the story. What do we have here? Well, we are rewriting it. We have a limit, h towards 0. And, well, we just repeat p of xo plus h times k of xo plus h. And now I'm adding 0. I'm adding 0, that means I'm not changing anything, so I'm subtracting p of xo times k of xo plus h, and I'm adding it at the same time. So I haven't changed anything, and still we have minus p of xo times k of xo, still in this numerator, divided over h. Alright, now we have a limit, h towards 0 still, and now you see my 0 was produced in such a way that I can take a common factors in both cases outside of the parentheses. So I take this one and that one outside of the parentheses. So I'm having k of xo plus h. I'm having p of xo plus h minus p of xo in the first place. And the last two terms, I have also a common factor, which is p of xo here and there. So I'm taking p of xo outside of the parentheses. I'm going to have k of xo plus h minus k of xo, and I still divide it by h. Now, if you remember what we've been doing with fractions, I can just split it exactly here. So I still have one huge limit. But now we're dealing with two fractions. The first one is k of xo plus h times p of xo plus h minus p of xo divided over h, plus we're having here p of xo times k of xo plus h minus k of xo divided over h. We close the parentheses. So what is the idea here? Well, the idea, we have a sum of two limits, and once again we can split the sum because of the sum rule of limits, as we proved previously or explained previously. In these cases I'm trying to avoid the word proving because it's not exactly the proof. It's just kind of visualization, or let's say putting it clear how it's working, but I'm not truly proving it since I need a bit more of mathematics. But I explained previously my point. All right, so we can split it if we do know that those two expressions do exist if we have limits. So we have a limit of h towards 0, k of xo plus h times of p of xo plus h minus p of xo divided over h, right? This is the first one, and there's going to be a second one, which is the limit h towards 0. Now we got p of xo times k of xo plus h minus k of xo divided over h. The question is it fine what I'm doing? So is it possible? Is it alright? And the answer is, we don't know yet, right? So this is the question mark, because we just do not know yet. We have to prove that those two limits really exist. Well, let's see. But it's not enough to see that with two limits, we're going to make it even smaller. So we have a product of two expressions, both with h, and we would like to take them apart. If you remember, it's only possible if those two limits do exist. Let's assume they do. We will see in a moment. So one more question mark. We have a limit h towards 0, k of xo plus h times a limit h towards 0 of p of xo plus h minus p of xo divided over h. This is how we do it. And then we have plus, and now you see, using the factor rule, I don't have to prove here anything because this value is not dependent on h. So I'm just kicking it outside of the limit because of the factor rule of the limits. So this is p of xo times limit h towards 0, k of xo plus h minus k of xo divided over h. And if you look at this is exactly the h-method definition, so the first principle of the derivative of k. And of course we assume that those two functions that we're working with are differentiable, right? So that means that limit exists easily. So this is k prime at xo. But what about this one? Well, this is also derivative of p of xo. That's nice. This one is already given. It's a set number. And this one can be easily computed, since if h is approaching 0, we're just getting to k of xo. So what we have is k of xo times p prime plus p of xo times k prime. I do not know why exactly, but kind of all around the world, all the teachers are using u and v. Well, these are most similar Latin letters that we can use. That's why I'm trying not to use them. But maybe at school you've seen u times v prime. So once again, don't get me wrong, but this is what you normally see at school maybe. U prime times v plus u times v prime. So that's the point, all right? And, well, we proved exactly that. You have the derivative of the first times the second unchanged plus the second derivative times the first unchanged. There you go. Let us see whether our example with x squared would be working now with this formula. So we had x squared prime. We know it is 2x. We're writing it as x times x. And so let us apply the product rule that we just proved. So we have x prime times unchanged x plus x times x second prime. It's going to be 1 times x plus x times 1. So it's x plus x. This is 2x. That seems to be working, right? So this is a product rule of the limits and the product rule of differentiation. Make sure you don't memorize the formulas. Try to understand it, and it will, well, simplify your approach to mathematics, but maybe also to life. At least it works for me. That's why I'm giving it to you. All the best, guys. See you in the next video. Bye-bye.